300,000 kilometers per second. That is the specific, magical figure that controls absolutely everything in our reality, from the microscopic atoms inside your own body to the largest, most sprawling galaxies in the universe. If you try to reach this speed, something truly terrifying takes place. You encounter something that completely goes against common sense and rewrites the fundamental rules of existence itself. Today, we are going to uncover exactly why the cosmos has established this barrier as absolutely unbreakable, and we will look at what actually happens when you dare to approach it. The truth of the matter is far stranger than any science fiction story you have ever heard. If you are fascinated by the deep mysteries of physics and the cosmos, please make sure to subscribe to this channel and give this video a thumbs up. And I have one quick question for you. If you could travel at the speed of light, where is the first place you would go? Let me know your answer in the comments section down below. I will pin the most creative answer I see. Now, let us begin. The story of exactly why we cannot travel at light speed begins with Albert Einstein's special theory of relativity, which was published in the year 1905. Before Einstein came along, scientists worked under the belief that space and time were fixed, unchanging stages where the events of the universe played out. However, Einstein revealed something far more bizarre. He showed us that space and time are actually interwoven into a single fabric known as spacetime. And this fabric operates by rules that seem to completely defy our common intuition. Let me paint you a vivid picture of what happens when you try to approach light speed. As you accelerate and go faster, something peculiar occurs. Your mass begins to increase. We are not talking about your physical size, but your mass, the very resistance you possess against being pushed. At 10% of the speed of light, this effect is barely noticeable. At 50%, you are approximately 15% more massive. But when you reach 90% of the speed of light, your mass has more than doubled. And as you creep even closer to light speed, reaching 99% or 99.9%, your mass skyrockets toward infinity. This is not just theoretical mathematics on a chalkboard. We observe this phenomenon every single day in our particle accelerators. The Large Hadron Collider located near Geneva accelerates protons to 99.9999% of the speed of light. At these incredible velocities, those tiny protons become 7,000 times more massive than when they are at rest. It takes the energy output of a small power plant just to nudge them that final tiny fraction closer to light speed. But this increase in mass is just the beginning of the weirdness. Time itself starts playing tricks on you. This phenomenon, which is called time dilation, means that as you travel faster, time passes more slowly for you compared to someone who is standing still. It sounds like pure science fiction, but it has been verified countless times. The GPS satellites orbiting the Earth currently have to account for this effect. Their clocks run faster than the clocks on the surface of the Earth because they are moving at high speed relative to us. Without correcting for relativistic time dilation, the GPS system would accumulate errors of about 10 kilometers per day. The implications become truly mind-boggling as you approach light speed. Imagine you are on a spacecraft traveling at 99.9% of the speed of light toward Proxima Centauri, our nearest star, which is 4.2 light-years away. From the perspective of Earth, your journey takes just over 4 years. But due to time dilation, you would experience the entire trip in just 2 months. If you push even closer to light speed, say to 99.999%, the journey shrinks to mere days from your perspective. This creates what physicists call the twin paradox. If you left Earth on a journey near the speed of light to a star 25 light-years away and then returned, 50 years would have passed back on Earth. But depending on how close to light speed you traveled, you might have aged only a few years. You would return home to find your twin sibling has become elderly, while you remained relatively young. This is not a thought experiment. It is the real consequence of how space-time functions. The energy requirements to achieve these speeds reveal another insurmountable barrier. To accelerate just 1 kilogram, about the weight of a small laptop, to 90% of the speed of light requires energy equivalent to the entire annual electricity consumption of a small country. Do you want to reach 99%? You will need 10 times more energy. 99.9%? That is another factor of 10. The energy requirement approaches infinity as you near light speed. Let us put this in perspective with real spacecraft. The fastest human-made object is the Parker Solar Probe, which reached speeds of about 195 kilometers per second as it fell toward the Sun. That sounds incredibly fast, and it is. You could circle the Earth's equator in about 3 minutes at that speed. But compared to light's 300,000 kilometers per second, Parker is crawling at just 0.065% of light speed. Even after decades of technological advancement, we are not even close to 1% of light speed. The Voyager 1 spacecraft, humanity's most distant ambassador, has been traveling for over 46 years and has reached a speed of about 17 kilometers per second. At this rate, it would take over 17,000 years just to travel one single light year. The gulf between our current capabilities and light speed is not just large, it is almost incomprehensibly vast. But here is where things get even stranger. As you accelerate toward light speed, space itself begins to contract in your direction of travel. This length contraction means that from your perspective, distances actually shrink. That 4.2 light-year journey to Proxima Centauri? At 99.9% of light speed, it appears to be only about 60 light days long from your viewpoint. The entire observable universe would compress into a thin disk in front of you as you approached light speed. This leads to a profound realization. From the perspective of light itself, no time passes at all. A photon emitted from a distant galaxy billions of light-years away experiences its entire journey across the vast cosmos in zero time. From the photon's frame of reference, it exists at its point of emission and its point of absorption simultaneously. This is why nothing with mass can reach light speed. It would require experiencing zero time, essentially existing outside of time itself. The relationship between energy and mass that Einstein discovered goes even deeper than simple acceleration. His famous equation, E equals mc squared, tells us that mass and energy are fundamentally the same thing in different forms. When you try to push something to light speed, you are not just fighting against its resting mass, you are fighting against all the energy you have already put into it, which manifests as additional mass. It is like trying to fill a bucket that gets heavier with every drop of water you add, eventually becoming so heavy you cannot lift the water to pour it in. This brings us to an interesting historical point. Scientists have known light has a finite speed for centuries, but measuring that speed precisely was one of humanity's greatest scientific challenges. Speaking of which, if you are curious about the ingenious methods scientists used throughout history to measure this cosmic speed limit, check out my video titled, "How was the speed of light measured?" Understanding how we discovered light speed helps us appreciate why it is such a fundamental barrier. The link is in the description below and on the card above. Now, let us talk about what happens to the space around you as you approach light speed. The universe would look increasingly bizarre. Due to relativistic aberration, the stars ahead of you would appear to crowd together into a bright circle, while the stars behind you would disappear into darkness. The colors would shift dramatically, too. Starlight ahead would blue shift toward higher frequencies, eventually becoming invisible gamma rays, while light from behind would red shift into invisibility. You would be flying blind through a universe transformed beyond recognition. The electromagnetic force itself starts behaving strangely at relativistic speeds. The magnetic field of a moving charged particle increases with velocity, approaching infinity as the particle nears light speed. This is why particle accelerators need exponentially stronger magnetic fields to bend the paths of particles traveling near light speed. The very forces that hold atoms together would distort and intensify in ways that make stable matter impossible at light speed. Consider what this means for a hypothetical light-speed spacecraft. Every atom in your body, every molecule in your ship, would experience these distortions. Chemical bonds would strengthen or weaken unpredictably. Electronic systems would fail as electrons behave in ways engineers never anticipated. The biological processes keeping you alive would cease to function. Approaching light speed is not just difficult, it is fundamentally incompatible with the existence of organized matter as we know it. There is another barrier we have not discussed yet: the interstellar medium. Space is not empty. Between stars, there is a thin soup of hydrogen atoms, dust particles, and cosmic rays. At normal spacecraft speeds, these pose minimal danger. But at relativistic speeds, each hydrogen atom hits with the force of a particle beam weapon. A dust grain would impact with the energy of a bomb. The faster you go, the more deadly space itself becomes. Scientists have calculated that at 99.9% of light speed, the collision with interstellar hydrogen would produce radiation equivalent to standing next to an unshielded nuclear reactor. The spacecraft would need impossibly thick shielding, which adds mass, which requires more energy to accelerate, which makes the whole endeavor even more impossible. It is a vicious cycle with no solution. Let us examine what current physics tells us about potential workarounds. You have probably heard of concepts like wormholes or warp drives, theoretical ways to travel faster than light without actually moving through space at light speed. While these ideas do not violate Einstein's equations, they require exotic matter with negative energy density, something that may not exist in nature. Even if it does, the amount needed would be astronomical, perhaps the mass-energy equivalent of the planet Jupiter, or more. The Alcubierre drive, proposed by physicist Miguel Alcubierre in the year 1994, is particularly fascinating. It would work by contracting space in front of a spacecraft and expanding it behind, creating a bubble that moves through space faster than light, while the ship inside remains stationary relative to its local space. The mathematics work out, but the energy requirements are beyond anything we could conceivably harness. We are talking about converting the mass of entire planets into pure energy. Another proposed method involves quantum entanglement. When particles are entangled, measuring one instantly affects the other, regardless of distance. This seems to violate the light speed limit. But there is a catch. No usable information can be transmitted this way. The results appear random until both parties compare notes through conventional, slower-than-light communication. The universe seems carefully designed to prevent any loophole that would allow faster-than-light information transfer. The fundamental issue is not just technological, it is woven into the fabric of causality itself. If you could travel faster than light, you could theoretically travel backward in time. This would create paradoxes. You could prevent your own birth, create logical contradictions, or violate the principle that causes must precede effects. The universe's speed limit is not arbitrary. It is what keeps reality consistent and logical. Recent experiments at CERN have pushed our understanding even further. When accelerating heavy ions instead of individual protons, scientists have observed that the nuclei actually flatten into pancake shapes due to length contraction. Gold nuclei, normally spherical, become disks less than 1 femtometer thick when traveling at 99.9% of light speed. This is not just theoretical. We can measure these shape distortions through the particles' collision patterns. The cosmological implications are equally profound. The expansion of the universe itself can carry distant galaxies away from us faster than light. But this does not violate relativity because the galaxies are not moving through space. Space itself is expanding between them. This means there are parts of the universe we will never be able to reach or even see, no matter how advanced our technology becomes. The observable universe has a hard boundary defined by light speed and cosmic expansion. Quantum mechanics adds another layer to the impossibility. The Heisenberg uncertainty principle states that you cannot simultaneously know a particle's exact position and momentum. As objects approach light speed, their momentum approaches infinity, which would make their position completely uncertain. According to quantum mechanics, the particle would effectively be everywhere and nowhere at once, a physical impossibility for any object with mass. The biological consequences of approaching light speed present another insurmountable barrier. Human bodies evolved in Earth's gentle gravitational field with its leisurely pace through spacetime. At relativistic speeds, every cell in your body would experience stresses that evolution never prepared us for. The calcium in your bones, the iron in your blood, the very DNA that makes you who you are, all would be subject to forces that could tear apart molecular bonds. Consider the effect on your cardiovascular system. Your heart pumps blood based on pressure differentials that assume normal physics. At relativistic speeds, the altered mass and time dilation would affect blood flow in unpredictable ways. Would your blood become more massive? Would chemical reactions in your cells slow down or speed up? We simply do not know because no living organism has ever experienced these conditions. But computer simulations suggest the results would be catastrophic. There is also the psychological aspect to consider. Imagine knowing that while you experience a journey of months, everyone you have ever known on Earth ages decades. This is not science fiction. It is the real consequence of time dilation. The emotional and mental toll of such temporal isolation would be unprecedented in human experience. You would return from your journey to find the world transformed, your loved ones aged or gone, and your culture changed beyond recognition. Let me share something that really drives home the impossibility: the energy density problem. As you pump more energy into accelerating an object, that energy does not just disappear, it adds to the object's relativistic mass. At speeds approaching light, you would need to concentrate so much energy in one place that you would risk creating a black hole. Yes, you heard that right. Trying to reach light speed could theoretically collapse your spacecraft into a singularity. The vacuum of space itself presents unexpected challenges at high speeds. Quantum field theory tells us that empty space is not really empty. It is filled with virtual particles constantly popping into existence and annihilating. At normal speeds, these quantum fluctuations are irrelevant. But at relativistic speeds, the Unruh effect predicts that you would perceive these fluctuations as real radiation. The faster you accelerate, the hotter this quantum bath would appear, eventually becoming lethal radiation that emerges from nothingness. Scientists have discovered another bizarre effect called relativistic beaming. As objects approach light speed, the radiation they emit becomes concentrated in a narrow cone in their direction of travel. This means a spacecraft's headlights would become a deadly beam of concentrated energy, while its engines would be nearly invisible from behind. Communication would become impossible as radio waves undergo the same beaming effect. The Parker Solar Probe, our current speed record holder, offers a sobering perspective. Despite using multiple gravity assists from Venus and falling deep into the Sun's gravity well, it barely scratches 0.1% of light speed. And this is after decades of engineering advancement and billions of dollars of investment. The gap between our best efforts and even 1% of light speed is humbling. Let us talk about the practical experiments that confirm these limitations. Cosmic rays, which are particles accelerated by supernovas and black holes, bombard Earth constantly. Some of these particles have energies that dwarf anything our accelerators can produce. The "Oh my God" particle, detected in 1991, had the kinetic energy of a baseball thrown at 60 miles per hour, all concentrated in a single proton. Yet even this incredibly energetic particle was traveling at 99.99999999999. 999999999% of light speed, still not quite reaching that ultimate barrier. The Global Positioning System provides daily proof of relativistic effects. GPS satellites orbit at about 14,000 kilometers per hour, which is nowhere near light speed. Yet they experience measurable time dilation. Their clocks run about 38 microseconds per day, faster than Earth clocks due to the combined effects of their speed and lower gravity. Engineers must constantly correct for this, or navigation errors would accumulate rapidly. If such tiny speeds cause measurable effects, imagine the impossibility of managing travel near the speed of light. Here is something that might blow your mind. From the perspective of a photon, the universe has zero size in its direction of travel. Length contraction is total at light speed. A photon emitted from a galaxy billions of light years away experiences its entire journey instantaneously. It exists at its point of creation and its point of absorption simultaneously. This is why mass cannot reach light speed. It would require existing in a state where distance has no meaning. The phenomenon of Cherenkov radiation demonstrates light's special status in another medium. In water or other transparent materials, light travels slower than its vacuum speed. Particles can actually travel faster than light in these media, creating a blue glow, which is the optical equivalent of a sonic boom. Nuclear reactors glow blue for this reason. But even here, nothing exceeds light's vacuum speed, the ultimate universal limit. Recent observations from the LIGO and Virgo gravitational wave detectors have confirmed another aspect of light speed limits. Gravitational waves, which are ripples in spacetime itself, travel at exactly the speed of light. When neutron stars collided 130 million light-years away, the gravitational waves and light from the event arrived within seconds of each other after traveling for over 100 million years. This confirms that light speed is not just about electromagnetic radiation. It is the fundamental speed limit for all information and causality in the universe. The search for tachyons, hypothetical particles that always travel faster than light, has turned up empty. If such particles existed, they would have imaginary mass and would require infinite energy to slow down to light speed. They would also travel backward in time, creating causality paradoxes. The universe seems carefully constructed to prevent such violations of causality. String theory, our best candidate for a theory of quantum gravity, suggests that light speed emerges from even more fundamental principles. In this framework, the universe has additional dimensions beyond the four we experience. Light speed might represent the maximum rate at which information can propagate through these higher dimensional spaces. It is not just a speed limit. It is a fundamental property of the geometry of existence itself. The economic reality of approaching light speed is equally prohibitive. Scientists have calculated that accelerating a small spacecraft weighing just 1,000 kilograms to 90% of light speed would require energy equivalent to the entire world's annual energy production for several years. And that is assuming perfect efficiency, which is impossible according to the laws of thermodynamics. The real energy requirement would be orders of magnitude higher. This brings us to the rocket equation problem. Every bit of fuel you carry adds mass, which requires more fuel to accelerate, which adds more mass, creating an exponential spiral. But chemical rockets reaching even 1% of light speed would require more fuel than exists in the entire solar system. Nuclear rockets might do better, but still fall catastrophically short. Even antimatter rockets, the most efficient theoretically possible, would need tons of antimatter to approach light speed. And we currently produce antimatter in quantities measured in individual atoms. The cosmic perspective reveals another limitation. The universe is expanding, and that expansion is accelerating due to dark energy. Galaxies beyond a certain distance are already receding from us faster than light. Not because they are moving through space that fast, but because space itself is expanding between us. Even if we could travel at light speed, most of the universe would remain forever unreachable. We are trapped in an ever-shrinking bubble of accessibility. Let us examine what happens to atoms themselves at relativistic speeds. The electrons orbiting atomic nuclei would experience different relativistic effects than the nuclei themselves. This could destabilize atoms, causing them to ionize or behave in unpredictable ways. The chemistry that makes life possible depends on precise electron configurations. At speeds approaching light, chemistry as we know it might simply cease to function. The Penrose-Terrell effect adds another layer of visual distortion. Objects moving at relativistic speeds do not just appear length contracted, they appear rotated. A cube flying past you at near light speed would seem to twist and turn, showing faces that should be hidden. This is not an optical illusion, but a real consequence of the finite speed of light from different parts of the object reaching your eye at different times. Consider the implications for navigation. At 99% of light speed, the entire visible universe would compress into a small circle ahead of you, blazing with blue-shifted radiation. Behind you, everything would disappear into darkness. Traditional navigation by stars would be impossible. You would be flying essentially blind, unable to see your destination or correct your course. The universe itself would become unrecognizable. The thermodynamic consequences are equally severe. The second law of thermodynamics states that entropy always increases. At relativistic speeds, the relationship between energy, temperature, and entropy becomes highly complex. Some calculations suggest that approaching light speed could create thermodynamic paradoxes where the normal flow of heat and the arrow of time become confused. The universe might prevent light speed travel simply to preserve thermodynamic consistency. Particle physics experiments have revealed another barrier: synchrotron radiation. When charged particles travel in curved paths at high speeds, they emit electromagnetic radiation. This is why particle accelerators glow with X-rays. At speeds approaching light, this radiation becomes so intense that particles lose energy as fast as you can supply it. It is like trying to fill a bucket with an ever-growing hole in the bottom. The Higgs field, which gives particles their mass, might play a role we do not fully understand. This field permeates all of space, and particles acquire mass by interacting with it. At relativistic speeds, the nature of this interaction might change in ways we have not yet discovered. Some theorists speculate that the Higgs field itself might provide a fundamental mechanism that prevents anything with mass from reaching light speed. Real spacecraft designs illustrate the impossibility. Project Orion in the 1960s proposed using nuclear explosions for propulsion. Even with thousands of nuclear bombs, it could only reach about 3 to 5% of light speed. Project Daedalus, a 1970s design using fusion rockets, might achieve 12% of light speed after decades of acceleration. We are not talking about small engineering improvements. We need revolutionary physics breakthroughs that may not be possible. The interstellar medium becomes increasingly hostile at high speeds. At 10% of light speed, hitting a single grain of dust would release energy equivalent to a large bomb. At 50% of light speed, the impact would be like a nuclear weapon. At 90%, even individual hydrogen atoms become deadly projectiles. Space itself transforms from an empty highway into a lethal shooting gallery. Quantum tunneling effects add complexity. At normal speeds, particles occasionally tunnel through energy barriers they should not classically be able to cross. At relativistic speeds, the probability of such tunneling events might change dramatically. This could affect everything from nuclear reactions to chemical bonds, making matter behave in ways we cannot predict or control. The communication problem is often overlooked. Even if we could travel at 99% of light speed, communicating with Earth would be nearly impossible. Signals would be extremely red-shifted or blue-shifted, making them hard to detect. Time dilation means a conversation would take years from Earth's perspective, but seem like moments to the travelers. You would be isolated not just by distance, but by the fundamental mismatch in the flow of time. Laboratory experiments with particle beams have revealed unexpected challenges. When two beams of particles traveling at 99% of light speed collide head-on, you might expect their relative velocity to be 198% of light speed. But relativistic velocity addition shows their relative speed is still just under light speed. The universe has built-in safeguards that prevent any observation of faster-than-light motion, no matter how you try to arrange it. The philosophical implications are profound. Light speed is not just a technical barrier. It fundamentally shapes the nature of causality, the structure of spacetime, and the possibility of knowledge itself. It ensures that causes precede effects, that information has limits, and that the universe maintains logical consistency. Without this cosmic speed limit, reality as we understand it would be impossible. The fundamental structure of spacetime itself rebels against light-speed travel. Einstein showed us that space and time are not separate entities, but aspects of a four-dimensional continuum. When you move through space, you are also moving through time. And your total velocity through spacetime always equals the speed of light. This means when you are sitting still, you are moving through time at light speed. As you accelerate through space, you must move slower through time to maintain that constant spacetime velocity. At light speed through space, you would stop moving through time entirely, a logical impossibility for anything that exists. This leads to one of the most mind-bending realizations in physics. Everything in the universe is always traveling at exactly the speed of light through spacetime. The difference is how that velocity is divided between space and time dimensions. Massive objects mostly travel through time with little spatial motion. Photons travel entirely through space with no passage through time. This is not just a mathematical quirk. It is the fundamental geometry of reality. Recent discoveries in quantum field theory have revealed another layer of impossibility. The quantum vacuum, what we call empty space, is actually teeming with virtual particles that pop into existence and immediately annihilate. At normal speeds, these fluctuations average out to zero. But the Unruh effect predicts that accelerating observers would perceive these fluctuations as real particles, creating a thermal bath of radiation. The acceleration needed to approach light speed would create a wall of quantum fire that would incinerate anything attempting to pass through. Let us talk about the gravitational implications. According to general relativity, mass and energy curve spacetime. As an object's kinetic energy approaches infinity near light speed, its gravitational field would become increasingly intense. Some calculations suggest that at sufficient speeds, you could create gravitational effects, comparable to a black hole. The universe might prevent light-speed travel simply to avoid these gravitational catastrophes. The discovery of the Higgs boson at CERN in the year 2012 confirmed how particles acquire mass. The Higgs field, which fills all of space, acts like cosmic molasses that slows down particles, giving them mass. Photons do not interact with the Higgs field, which is why they can travel at light speed. Everything else gets bogged down to varying degrees. This is not just a speed limit. It is a fundamental mechanism built into the fabric of reality itself. Consider what neutrinos teach us about near-light speed travel. These ghostly particles have tiny but non-zero mass, forcing them to travel slightly slower than light. In the famous supernova observation of 1987, neutrinos arrived at Earth about 3 hours before the visible light. Not because they traveled faster, but because they escaped the collapsing star's core immediately, while light took hours to work its way out. Even with their minuscule mass, neutrinos cannot quite reach light speed, approaching it only because their mass is millions of times smaller than electrons. The practical consequences for space exploration are sobering. Even if we could somehow achieve 10% of light speed, far beyond our current capabilities, a journey to Proxima Centauri would take over 40 years. The crew would need life support, food, water, and fuel for decades. Equipment would degrade, people would age, and the psychological challenges of such isolation would be unprecedented. And that is just to reach our nearest neighbor. The galaxy is 100,000 light-years across. Metamaterials research has revealed interesting properties of light propagation. Scientists have created materials with negative refractive indices that bend light backward, and others that slow light to a crawl. But even in these exotic materials, nothing actually exceeds light's vacuum speed. The universe seems to have multiple backup systems, ensuring nothing breaks this ultimate limit. The cosmic microwave background radiation presents another challenge. This afterglow of the Big Bang fills all of space with low-energy photons. At relativistic speeds, blue shifting would transform this gentle radiation into a deadly gamma-ray bombardment. Calculations show that at 99.9% of light speed, the cosmic microwave background would deliver radiation doses that would kill a human in seconds. The universe's baby picture becomes a death ray for would-be light-speed travelers. Time crystals, discovered in the year 2016, show that even exotic states of matter respect fundamental limits. These structures repeat in time, rather than space, seeming to violate thermodynamics by exhibiting perpetual motion. but closer examination shows they still obey all physical laws, including the speed of light limit. Even matter in its strangest forms cannot escape universal constraints. The quantum Zeno effect demonstrates how observation itself might prevent reaching light speed. In quantum mechanics, frequently observing a system can freeze its evolution. As particles approach light speed, their interaction with the quantum vacuum effectively observes them continuously, potentially creating a fundamental quantum mechanical barrier to further acceleration. The universe might be constantly watching, preventing its own rules from being broken. Astronomical observations provide natural experiments in relativistic physics. Jets from quasars and active galactic nuclei shoot out at 99.9% of light speed or higher. We can observe these cosmic particle beams across billions of light years, studying what happens when nature pushes against the ultimate speed limit. Even with the entire energy output of supermassive black holes driving them, these jets never quite reach light speed. The information paradox adds another dimension to the impossibility. Information itself cannot travel faster than light. This is not just about physical objects, but about cause and effect, knowledge, and the very possibility of communication. If information could exceed light speed, you could send messages into the past, creating grandfather paradoxes and logical contradictions. The universe's speed limit preserves not just physical consistency, but logical coherence. Laboratory experiments with Bose-Einstein condensates have created conditions where light itself slows to walking speed or even stops entirely. But this is not violating any limits. The photons are being absorbed and re-emitted by atoms in the condensate. The information still cannot exceed light's vacuum speed. Even when we manipulate light itself, we cannot break the universal rules. The holographic principle suggests that all information in a volume of space can be encoded on its boundary. This deep connection between information, entropy, and geometry might explain why light speed is what it is. The maximum rate of information flow might be determined by fundamental properties of spacetime geometry that we are only beginning to understand. The role of dark matter and dark energy in limiting light speed travel adds another layer of mystery. Dark energy, which makes up about 70% of the universe's energy density, is causing cosmic expansion to accelerate. This means distant galaxies are not just far away. They are getting farther every second, and most are already receding faster than light due to space expansion. Even if we could travel at light speed, we would be forever locked out of most of the observable universe, watching helplessly as galaxies disappear beyond the cosmic horizon. Quantum entanglement seems to mock the light speed limit, with entangled particles instantly correlating regardless of distance. Einstein called this spooky action at a distance, and it bothered him deeply. Modern experiments have confirmed that entanglement is real. But here is the crucial detail. No information actually travels faster than light. The correlations are instant, but they are random until both parties compare results through conventional, slower-than-light channels. The universe permits instant correlation, but forbids instant communication, preserving causality with elegant precision. The anthropic principle offers a different perspective on why light speed must be limited. If light traveled infinitely fast, electromagnetic forces would propagate instantaneously, making stable atoms impossible. Chemical reactions would happen instantly, or not at all. The delicate dance of electrons around nuclei that makes chemistry, and therefore life, possible requires finite light speed. We exist because light speed has exactly the value it does. Change it even slightly, and the universe becomes hostile to complexity. Consider what we have learned from studying pulsars, which are rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. Some pulsars spin hundreds of times per second, with their surfaces moving at significant fractions of light speed. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. Its equator travels at about 24% of light speed. Any faster, and the neutron star would tear itself apart. Even these extreme objects with gravity billions of times stronger than Earth's cannot push matter beyond certain speeds. The firewall paradox in black hole physics reveals deep connections between light speed information and the structure of spacetime. At a black hole's event horizon, space is falling inward at light speed. This is why nothing can escape. You would need to travel faster than light just to stay still. Recent theoretical work suggests that event horizons might be surrounded by firewalls of high-energy radiation created by the breakdown of quantum entanglement. These ideas hint at profound connections between light speed, quantum mechanics, and gravity that we are only beginning to understand. Cosmic strings, if they exist, would be defects in spacetime itself, remnants from phase transitions in the early universe. These hypothetical objects would be thinner than atoms, but potentially light-years long with immense mass. Some theories suggest cosmic strings could enable faster-than-light travel by creating closed time-like curves, but every investigation finds the same result. Any configuration that allows faster-than-light travel also creates paradoxes that would destroy causality. The universe seems designed to prevent its own logical contradiction. The delayed choice quantum eraser experiment demonstrates how light speed limits affect quantum mechanics. In this experiment, the decision to observe or not observe particle properties can seemingly change the past behavior of photons. But careful analysis shows no information, travels backward in time. The speed of light limit ensures that quantum mechanics, as weird as it is, never violates causality. The universe permits quantum strangeness, but draws the line at faster-than-light information transfer. Let us examine what happens at the Planck scale, the smallest possible distance that has physical meaning, about 10 to the power of -35 meters. At this scale, quantum effects dominate, and spacetime itself might become discrete rather than continuous. Some theories suggest that light speed represents the maximum rate at which changes can propagate through this quantum foam. It is like the universe has a maximum refresh rate, and light speed is it. The false vacuum hypothesis adds an existential dimension to light speed limits. Our universe might exist in a metastable state, like water that is supercooled below freezing, but has not turned to ice yet. If our vacuum state is not the lowest possible energy state, it could potentially decay to a lower state, destroying everything we know. This vacuum decay would propagate at exactly light speed, giving no warning. The same limit that prevents us from exploring the stars also determines how fast the universe could potentially end. Observations of gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, provide natural experiments in extreme physics. These explosions accelerate particles to 99.999% of light speed or higher. Yet, even with the energy of entire stars converted to kinetic energy in seconds, nothing breaks the light barrier. Nature shows us that even the most violent events in the cosmos respect this fundamental limit. The concept of rapidity in special relativity offers another perspective. While velocity is limited to light speed, rapidity, a measure of motion that accounts for relativistic effects, can increase without bound. But infinite rapidity still corresponds to exactly light speed, never exceeding it. It is as if the universe has multiple mathematical frameworks all conspiring to enforce the same limit. Warp drive research, while highly speculative, has revealed interesting theoretical possibilities. The Alcubierre metric shows that general relativity permits spacetime geometries where effective faster-than-light travel might be possible. But every proposed implementation requires exotic matter with negative energy density, something that may not exist. Even if it does, recent calculations show that quantum effects would likely destroy any warp bubble before it could form. The universe seems to close every loophole, no matter how clever. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics prevent time travel on macroscopic scales. Since faster-than-light travel would enable time travel, this conjecture implies that nature must forbid exceeding light speed. Hawking suggested that quantum effects would destroy any would-be time machine, creating infinite energy densities that prevent the formation of closed time-like curves. Studies of superfluids and superconductors have revealed that even exotic states of matter respect fundamental limits. In these materials, particles form collective quantum states with remarkable properties: zero viscosity, perfect conductivity, and other seemingly impossible behaviors. Yet, even in these quantum materials, information and energy still cannot propagate faster than light. The speed limit holds even when matter behaves in its strangest ways. The computational perspective reveals another fundamental barrier. The universe might be computing its own evolution with light speed, representing the maximum rate at which information can be processed. From this viewpoint, trying to exceed light speed would be like trying to make a computer run faster than its clock speed. Not just difficult, but meaningless. Every interaction between particles, every quantum state change, every moment of existence unfolds at a rate governed by this cosmic clock speed. Recent experiments with quantum computers have shown that even quantum information processing cannot escape light speed limits. While quantum computers can solve certain problems exponentially faster than classical computers through superposition and entanglement, they still cannot transmit results faster than light. The quantum advantage comes from parallel processing, not from breaking speed limits. The universe permits computational shortcuts, but maintains strict limits on information propagation. The discovery of time dilation near massive objects adds another dimension to the impossibility. GPS satellites must account not just for their orbital speed, but also for their altitude above Earth's gravitational well. Time runs faster in weaker gravity, adding about 45 microseconds per day to satellite clocks. Near a black hole, time dilation becomes extreme. At the event horizon, time stops relative to outside observers. This gravitational time dilation combines with velocity time dilation to create an even more complex barrier to light speed travel. Let us consider what cosmic rays teach us. The highest energy cosmic ray ever detected, dubbed the "Oh my God" particle, carried the energy of a baseball pitched at 60 miles per hour, all in a single proton. This particle was traveling at 99, followed by 22 more 9% of light speed. Yet, even with energy that defies comprehension, it still fell short of the ultimate barrier. If the universe's most violent events cannot push particles to light speed, what hope do human technologies have? The vacuum birefringence effect, recently observed around neutron stars, shows how extreme conditions affect light propagation. In the intense magnetic fields near these objects, billions of times stronger than anything on Earth, empty space itself becomes polarized, affecting how light travels. Yet even in these extreme conditions where spacetime itself is twisted and polarized, nothing exceeds the fundamental speed limit. The universe maintains its rules even in the most exotic environments. observations of distant supernovae revealed that the universe's expansion is accelerating, earning the 2011 Nobel Prize in Physics. This discovery means that galaxies beyond a certain distance are already unreachable. Even if we could travel at light speed, with each passing moment, more of the universe slips beyond our cosmic horizon, forever lost to us. The observable universe is shrinking, not in size, but in terms of what we could potentially visit or communicate with. The frame dragging effect, predicted by general relativity and confirmed by the gravity probe B satellite, shows how rotating massive objects drag spacetime around with them. Near a rotating black hole, space itself is twisted and pulled around. In the ergosphere, a region outside the event horizon, space is dragged faster than light relative to distant observers. Yet nothing can actually exceed light speed locally. Even when spacetime itself is being twisted and dragged, the fundamental limit remains inviolable. Quantum chromodynamics, the theory of the strong nuclear force, reveals why quarks can never be isolated. As you try to pull quarks apart, the energy you add creates new quark-antiquark pairs, rather than separating the original quarks. This confinement is absolute. No amount of energy can isolate a quark. Similarly, no amount of energy can push mass to light speed. Both represent fundamental barriers that nature simply will not let us cross. The Maxwell equations that govern electromagnetism naturally predict electromagnetic waves traveling at light speed. This is not a coincidence. It is a deep truth about the nature of electric and magnetic fields. Change the speed of light, and you would have to change the fundamental nature of electromagnetism, which would change chemistry, which would change everything. The speed of light is not just a speed limit. It is woven into the equations that describe how forces work. Studies of binary pulsars have confirmed general relativity's predictions to extraordinary precision. The Hulse-Taylor pulsar system loses energy exactly as predicted by gravitational wave emission. These observations, spanning decades, show that gravity itself propagates at light speed. When massive objects accelerate, the changes in the gravitational field ripple outward at the speed of light, never faster. Even gravity, the force that shapes the cosmos, respects the universal speed limit. The concept of proper time reveals why light speed travel would mean stepping outside of time itself. Proper time is the time experienced by an object along its path through spacetime. For massive objects, proper time always passes, but for anything traveling at light speed, proper time stops. This is not time dilation. It is the complete absence of time. 2. Travel at light speed would mean experiencing zero time, existing outside the temporal dimension entirely. Laboratory experiments with ultra-intense lasers have created some of the most extreme conditions ever achieved on Earth. The extreme light infrastructure can produce laser pulses with intensities that literally tear apart empty space, creating electron-positron pairs from pure energy. Yet even these conditions, where the fabric of spacetime is stressed to its limits, cannot accelerate particles beyond light speed. We can rip apart the vacuum itself, but we cannot break its speed limit. The phenomenon of Hawking radiation demonstrates how even black holes respect light speed limits. Black holes evaporate by emitting radiation, with smaller black holes radiating faster. This radiation emerges from just outside the event horizon, where virtual particle pairs are separated by the intense gravitational field. One particle falls in, while the other escapes at speeds approaching but never reaching light speed. Even at the edge of a black hole, where spacetime is maximally curved, nothing breaks the cosmic speed limit. The search for Lorentz invariance violations Any evidence that the laws of physics might change at different speeds or energies has found nothing. Experiments ranging from tabletop laser systems to observations of gamma rays from distant galaxies all confirm that physical laws remain exactly the same, regardless of motion. The universe's rules are perfectly consistent with light speed as the unchanging constant that ties everything together. The relationship between entropy and information provides yet another barrier to light speed travel. According to the second law of thermodynamics, entropy always increases in isolated systems. But information theory tells us that information and entropy are fundamentally related. Erasing information increases entropy. As objects approach light speed, the information required to describe their quantum states approaches infinity. The universe might prevent light speed travel simply to avoid infinite information density, which would violate thermodynamic principles. Consider the practical impossibility from an engineering standpoint. The International Space Station, humanity's most ambitious space construction, orbits at about 7.66 kilometers per second, just 0.0025% of light speed. It took dozens of launches, hundreds of billions of dollars, and decades of international cooperation to achieve this. To reach even 1% of light speed would require energy and engineering capabilities roughly 400,000 times greater. The gap between our current abilities and light speed is not just large, it is astronomical. The discovery of dark matter's gravitational effects adds complexity to the challenge. Dark matter, which outweighs normal matter 5 to 1, creates invisible gravitational fields throughout space. Any spacecraft approaching light speed would have to navigate through these invisible gravitational wells and currents. It is like trying to sail through an ocean where most of the waves and currents are invisible, constantly pulling you off course with forces you cannot see or predict. Plasma physics at relativistic speeds presents unique challenges. As particles approach light speed, their electromagnetic fields become compressed and intensified in the direction of motion. This creates non-linear effects where particles interact with their own fields in complex ways. Plasma instabilities that are manageable at normal speeds could become catastrophic at relativistic velocities, potentially destroying any spacecraft from within through uncontrollable electromagnetic oscillations. The Casimir effect demonstrates that even empty space has structure and energy. Between closely spaced conducting plates, certain wavelengths of quantum fluctuations are excluded, creating a measurable force. At relativistic speeds, the interaction with quantum vacuum fluctuations would be dramatically altered. Some calculations suggest this could create a kind of quantum friction that increases exponentially as you approach light speed, making further acceleration impossible. Recent observations of fast radio bursts, mysterious millisecond pulses from distant galaxies, provide natural experiments in light-speed physics. These signals travel billions of light years, allowing us to test whether different frequencies of electromagnetic radiation travel at different speeds. So far, all observations confirm that radio waves, visible light, X-rays, and gamma rays all travel at exactly the same speed. See, the universe's speed limit is truly universal. The twin paradox becomes even more extreme when we consider realistic scenarios. The journey to the Andromeda Galaxy at 99.99% of light speed would take about 2.5 million years from Earth's perspective, but only 50,000 years for the travelers due to time dilation. They would return to an Earth 5 million years in the future, where humanity might have evolved into something unrecognizable or gone extinct entirely. The isolation would not just be spatial, but temporal, cutting travelers off from their entire species' timeline. Metamaterial research has revealed fascinating properties, but no violations of fundamental limits. Scientists have created materials that bend light backward, slow it to a crawl, or even stop it entirely. But in every case, information still cannot travel faster than c. These materials manipulate the phase velocity or group velocity of light. But the front velocity, the speed at which information actually propagates, never exceeds the fundamental limit. The role of virtual particles in creating mass reveals another aspect of the light speed barrier. The strong force that binds quarks in protons and neutrons is mediated by virtual gluons. These virtual particles contribute most of a proton's mass through their kinetic energy. As particles approach light speed, the virtual particle cloud around them becomes increasingly complex and energetic, contributing to the exponential increase in relativistic mass. Studies of pulsar timing arrays have placed stringent limits on any possible variations in fundamental constants, including light speed. By monitoring the incredibly regular pulses from millisecond pulsars over decades, astronomers can detect tiny changes in the laws of physics. These observations show that light speed has remained constant to better than 1 part in a billion over cosmic time. The universe's speed limit is not just universal in space, it is constant throughout time. The concept of the Rindler horizon illustrates how acceleration itself creates boundaries. A constantly accelerating observer experiences an event horizon behind them, a boundary beyond which no signal can ever catch up. As acceleration increases toward what would be needed for light speed, this horizon approaches the observer. At infinite acceleration required for instant light speed, the horizon would engulf them entirely, cutting them off from the entire universe. Quantum field theory in curved spacetime predicts that extreme accelerations would create particle production from the vacuum. The Unruh radiation that accelerating observers perceive would become increasingly intense as speeds approach c. At sufficient acceleration, this radiation would be energetic enough to create particle-antiparticle pairs, which would create more radiation, potentially leading to a runaway process. The vacuum itself might prevent light-speed travel through catastrophic particle production. The holographic principle suggests that the information content of any region is limited by its surface area, not its volume. This implies fundamental limits on information density and processing speed. Since approaching light speed requires processing increasingly complex quantum states, there might be a holographic bound that prevents the information density needed for light speed travel. The universe's information processing limits might be the ultimate barrier. Observations of cosmic voids, vast empty regions between galaxy clusters, show that even in the emptiest parts of space, virtual particles and quantum fields exist. A spacecraft at relativistic speeds would interact with these fields in unprecedented ways. The quantum vacuum that seems empty at rest becomes a complex dynamic medium at high speeds, potentially creating unexpected forces and interactions that our current physics cannot fully predict. The discovery of the accelerating expansion of the universe means that light speed is not even fast enough to explore most of the cosmos. Galaxies beyond the cosmic horizon are receding faster than light due to space expansion. Even if we could travel at light speed, we would be confined to an ever-shrinking bubble of reachable space. The universe has not just set a speed limit. It is structured so that most of it will forever remain beyond our reach. The emergence of time itself from quantum entanglement offers a revolutionary perspective on light speed limits. Recent theoretical work suggests that time might not be fundamental, but emerges from correlations between quantum systems. In this view, the speed of light represents the maximum rate at which quantum correlations can establish the flow of time. Exceeding light speed would not just be impossible, it would be meaningless in a universe where time itself depends on staying below this cosmic threshold. Let us examine what happens to fundamental forces at relativistic speeds. The electromagnetic force mediated by photons already operates at light speed. But the weak nuclear force responsible for radioactive decay is mediated by massive W and Z bosons that travel slower than light. At relativistic speeds, the interplay between these forces would be dramatically altered. Radioactive materials might decay at different rates. Chemical bonds might strengthen or weaken unpredictably. And the delicate balance that allows atoms to exist could be disrupted. The phenomenon of relativistic reconnection in astrophysical jets shows nature pushing against the speed limit. In these cosmic particle accelerators, magnetic field lines break and reconnect at speeds approaching c, launching particles to incredible energies. Yet, even with magnetic fields millions of times stronger than Earth's and energies that dwarf our biggest accelerators, these natural systems cannot break the barrier. They approach it asymptotically, getting closer but never reaching it, like a mathematical curve approaching but never touching an axis. Consider the implications for consciousness itself. Our thoughts are patterns of electrical activity in neural networks ultimately limited by the speed of electromagnetic signals. Some philosophers and physicists speculate that consciousness might depend on quantum processes in the brain. If so, the speed of light does not just limit how fast we can travel. It might fundamentally limit how fast we can think, process information, or experience reality. The cosmic speed limit might be intimately connected to the nature of awareness itself. The discovery of topological insulators and other exotic materials has revealed new states of matter with unique properties. In these materials, electrons can flow without resistance along surfaces, while the interior remains insulating. Some theorists hoped these might provide loopholes for faster-than-light information transfer. But experiments confirm that even in these exotic states, information propagation respects the universal limit. Nature seems to have closed every possible loophole. Gravitational lensing observations provide natural tests of light speed constancy across cosmic distances. Light from distant quasars bent around intervening galaxies creates multiple images that arrive at different times. By comparing these arrival times with the geometry of the lensing system, astronomers can test whether light speed varies with energy or distance. All observations confirm that light speed remains exactly constant across billions of light-years and vast ranges of photon energy. The quantum Zeno paradox reveals how observation itself might enforce the speed limit. In quantum mechanics, frequently measuring a system can freeze its evolution, the watched pot that never boils. As particles approach light speed, their increased interaction with virtual particles and quantum fields effectively measures them more frequently. This continuous observation might create a fundamental quantum barrier that becomes infinitely strong at light speed. Studies of neutron star mergers have confirmed that gravitational waves travel at exactly light speed. The LIGO and Virgo detectors observed gravitational waves from colliding neutron stars 130 million light-years away, with electromagnetic signals arriving within seconds. After traveling for over 100 million years, both types of waves arrived nearly simultaneously, confirming that gravity and light respect the same cosmic speed limit to extraordinary precision. The concept of emergent spacetime in quantum gravity theory suggests that space and time themselves might not be fundamental, but emerge from more basic quantum structures. In loop quantum gravity, spacetime is woven from discrete quantum threads. In this picture, Light speed might represent the maximum rate at which changes can propagate through this quantum fabric, like the maximum speed of sound in a material, but for the fabric of reality itself. The firewall paradox in black hole physics illustrates deep connections between light speed, quantum mechanics, and information. Some theories suggest that black hole event horizons are surrounded by high-energy firewalls that destroy anything falling in. These firewalls would exist precisely at the boundary where escape velocity equals light speed. The cosmic speed limit might be fundamentally connected to the preservation of quantum information and the resolution of black hole paradoxes. Observations of the cosmic web's large-scale structure reveal that even the universe's biggest patterns respect light speed limits. Galaxy clusters and superclusters form through gravitational attraction, limited by how fast gravity propagates at light speed. The filament structure we observe represents the maximum complexity that could develop given the finite speed of gravitational interaction over cosmic time. A universe with infinite light speed would look completely different. The phenomenon of vacuum decay presents an existential connection to light speed. If the Higgs field is not in its lowest energy state, a bubble of true vacuum could form and expand, destroying everything we know. This bubble would expand at exactly light speed, no faster, no slower. The same cosmic speed limit that prevents us from exploring the stars also determines the maximum speed at which the universe could potentially end. Recent experiments with optomechanical systems have achieved unprecedented control over the interaction between light and mechanical motion. Scientists can now cool mechanical oscillators to their quantum ground state using light and observe quantum effects in objects visible to the naked eye. Yet even in these systems where classical and quantum mechanics merge, the speed of light remains an absolute barrier. Information encoded in either light or mechanical motion cannot exceed c. The relationship between complexity and light speed suggests deep principles. Complex systems require time for information to flow between components. At light speed, time dilation becomes infinite, freezing all processes. This might not be coincidental. The universe might require a finite speed limit to allow complexity, computation, and ultimately consciousness to exist. Without the light speed limit, the universe might be simpler, but also sterile and unchanging. Studies of quantum error correction in nature reveal that the universe has built-in mechanisms to preserve information despite quantum uncertainty. These error-correcting codes might also play a role in enforcing the speed limit. Any attempt to exceed light speed might trigger error correction mechanisms that prevent the violation. Similar to how quantum error correction preserves quantum information in quantum computers. The anthropic principle takes on new meaning when we consider light speed. We exist in a universe with this particular speed limit not by chance, but by necessity. In hypothetical universes with different light speeds, the fundamental forces would be imbalanced. Electromagnetic forces might overpower nuclear forces, preventing stable atoms, or gravity might be too weak to form stars and galaxies. The precise value of c creates a cosmic sweet spot where complexity can emerge and evolve into conscious beings capable of pondering their own existence. Recent philosophical discussions about the nature of physical laws suggest that the speed of light might be more than just a constant. It might be a logical necessity. Just as mathematical truths like pi or the square root of 2 emerge from the structure of mathematics itself, light speed might emerge from the logical structure of any consistent physical reality. In this view, asking why we cannot exceed light speed is like asking why we cannot make a square circle. It is not physically impossible, but logically incoherent. The simulation hypothesis offers another perspective. If our universe is a computed reality, then light speed might represent the maximum rate at which the underlying computational substrate can process information. Every interaction between particles, every quantum event, every moment of existence would be computed at this fundamental clock rate. Trying to exceed light speed would be like trying to make a computer program run faster than the processor it is running on. Not just impossible, but meaningless within the system. Consider the cosmic perspective on human ambitions. Yes, the light speed limit means we will likely never visit other stars in person, never spread across the galaxy like science fiction promises. But it also means we are protected from causality paradoxes, from a universe where effect could precede cause. It ensures that time has meaning, that stories have beginnings and endings, that existence unfolds in an ordered way that consciousness can comprehend and appreciate. The discovery of gravitational waves has opened new windows into understanding cosmic limits. These ripples in spacetime carry information about the universe's most violent events, colliding black holes, neutron star mergers, perhaps even echoes from the Big Bang itself. Yet they too travel at exactly c, confirming that the speed limit applies not just to matter and energy, but to the fabric of space and time. The universe speaks to us through these waves, but even its most fundamental messages cannot exceed the cosmic speed limit. Looking toward the future, various proposed technologies might seem to offer hope for faster-than-light travel. Alcubierre drives, traversable wormholes, quantum entanglement. Each captures our imagination. But deeper investigation always reveals the same truth. The universe has carefully closed every loophole. These exotic solutions either require impossible conditions, create paradoxes, or simply do not work as hoped. The speed limit is not an engineering challenge to be solved, but a fundamental aspect of reality to be accepted. The emotional and philosophical implications run deep. Knowing that most of the universe will forever remain beyond our reach can feel limiting, even tragic. Galaxies we see today will eventually disappear beyond the cosmic horizon, lost to accelerating expansion. Future civilizations might look out at an empty sky, unaware of the cosmic richness we can still observe. Yet, this limitation also makes our moment in cosmic history special. We live in an era when we can still see and study much of the universe, even if we cannot visit it. The search for extraterrestrial intelligence takes on new meaning in light of these limits. If alien civilizations exist, they face the same constraints we do. No galactic empires spanning thousands of light-years with faster-than-light communication. Instead, intelligence might be scattered in isolated islands, each alone in their region of space, perhaps sending messages that take millennia to cross the voids. The universe's speed limit does not just isolate us, it isolates everyone. Yet there is profound beauty in these limitations. The finite speed of light means when we look at the night sky, we are seeing history. The moon as it was a second ago, the sun 8 minutes in the past, the nearest stars years ago, distant galaxies billions of years in their youth. We have access to the universe's entire history written in light. If light traveled infinitely fast, we would see only the present. No cosmic archaeology, no baby pictures of galaxies, no direct observation of how the universe evolved. The quantum mechanical aspects of the light speed limit reveal the universe's deep interconnectedness. Every particle knows about every other particle through fields that propagate at c. Changes ripple outward in expanding spheres of causality, weaving the separate into the connected. The speed limit does not isolate parts of the universe. It defines how they communicate, creating the cosmic web of cause and effect that links all existence. As our technology advances, we will continue to push against this barrier, and we should. Each attempt teaches us more about the universe's structure. Particle accelerators approaching ever closer to C reveal new physics. Spacecraft achieving higher fractions of light speed would open the solar system to human exploration. The journey toward the impossible destination is valuable even if the destination itself remains forever out of reach. In the end, the impossibility of light-speed travel teaches us humility and wonder in equal measure. We are finite beings in a universe with finite limits. Yet we have managed to understand those limits through observation, mathematics, and reason. We may never travel to the stars, but we can know them through their light. We may never break the cosmic speed limit, but we can understand why it exists and appreciate its role in making our existence possible. The universe has given us a gift in the speed of light, not a barrier, but a foundation. It is the cosmic constant that ensures causality, enables time, permits complexity, and allows conscious beings to emerge and ponder their place in the grand scheme. We are made of star stuff, limited by light speed, yet capable of understanding both our cosmic origins and our physical constraints. In that understanding lies not disappointment, but a deeper appreciation for the elegant, consistent, and beautiful universe we inhabit. So the next time you look at the stars, remember their light reaches you at the only speed the universe allows, carrying messages across the cosmic gulf. You will never visit them, but you are connected to them through the constant dance of electromagnetic waves. That is not a limitation. That is the universe revealing its deepest nature to anyone curious enough to look up and wonder. If you made it this far, make sure to subscribe to the channel and give this video a thumbs up. And if you enjoyed this video, I am sure you will love this other one on the left side of the screen, titled "What if the speed of light changed?" Discover why even a tiny change in light speed would unravel atoms, destroy stars, rewrite the laws of physics, and reshape the entire cosmos. See you there.